welcome to Badger Talks Live, which brings exciting happenings, resources, and talent from your UW flagship campus to the people of Wisconsin and beyond. I'm Sarah Kubiak, originally from Janesville, Wisconsin. I'm a junior studying astrophysics and life science communication. I'm also a Letters and Sciences Dean's Ambassador, where I met and now work directly with Dean Wilcots to foster community between students and alumni, as well as celebrate all the great things the college has done. I'm pleased to introduce Eric Wilcots, Dean of the College of Letters and Sciences and the Mary C. Jacoby Professor of Astronomy. Today, Eric will be taking us on a journey through space to explore the matter between galaxies and how that matter informs their creation and evolution. In addition to his many responsibilities as Dean of the largest college on the UW-Madison campus, Eric's astronomical work and research focuses on the evolution and environment of galaxies and groups in which they reside through the lens of radio wavelengths. Prior to moving to Madison, he was a Carl Janksy postdoctoral fellow at the National Radio Astronomy Observatory in Socorro, New Mexico, and he continues that line of research through the UW's involvement in the Southern African Large Telescope Project, the largest single aperture optical telescope in the Southern Hemisphere. Please welcome Eric Wilcots.
Great, thank you, Sarah, and thank you all for joining us for this Badger Talks Live. Appreciate the invitation to be here, and I hope you enjoy the next 30 to 40 minutes as we take a journey through something that I find particularly really fascinating in thinking about how galaxies evolve and what's in between them. Before I get started, I've got my title slide up here on the screen, and I just want to point out that an amazing thing about science today, and this is not just true of astronomy, but really any scientific endeavor, is that it is remarkably collaborative. And so the work that I'm going to be talking about that I have the privilege to work on has been done with a number of students over the years, as well as large teams of collaborators, our team Jets and our team Chilies, and I'll talk about that a little bit later on. But I do want you to get the sense and the understanding that science today is remarkably collaborative, and it takes a lot of people. And that doesn't count all of the folks it takes to put together the technology that we need to advance science. So keep that in mind as we go along. So I want to start with this slide, and I hope your room, wherever you are watching this, is dark enough to appreciate this picture. This is a picture of the night sky taken from South Africa. The structure you see in the foreground there is actually the dome of the Southern African Large Telescope, just outside of the town of Sutherland in the Karoo region of South Africa. As Sarah mentioned, it's the largest single aperture optical telescope in the Southern Hemisphere. And this picture shows you the night sky in all of its glory as seen from the site of the telescope. And it takes us back to a time long ago when we as humans looked to the night sky as a source of our stories, as a source of inspiration. And the patterns that we saw in the night sky were the patterns that led us to think about who we are as humans and our place in the universe. What you see here is somewhat familiar to many of you if you've been able to get away from the city lights and get out to a nice dark spot to look at the night sky. Lots of stars, right? Almost everything you see here, every dot is a star. And then there's this sort of faint glow, this band that goes across the image. And that is something that we call the Milky Way. And we're going to talk about that in a little bit more. You also notice that there's some darker regions in that thing we call the Milky Way. And for many of the indigenous peoples in the Southern Hemisphere, particularly indigenous peoples of Australia, their stories of the night sky were told primarily around these dark regions that you see in the night sky because they are so stark. And so if you've had the opportunity to travel to the Southern Hemisphere and really admire the night sky from the Southern Hemisphere, you'll see why those regions of the sky led to a number of the stories that we see in that indigenous folklore. So astronomers 120 years ago, 100 years ago, understood the night sky and understood the things that were in the night sky. Telescopes had been around for a while, and they had identified a number of things. One of the things that struck astronomers as interesting 120 years ago was this object known as the Great Spiral Nebula in Andromeda. So it's in the constellation Andromeda, and you see a picture of it here. We also know of it as M31. And astronomers of the day were puzzled by this particular object because it didn't quite look like anything else that they could identify. It didn't quite look like a star. It's obviously very elongated and fuzzy and extended. So it didn't have the shape of the star. But its spectrum, that signature of its light as a function of wavelength, looked to be sort of a mixture of what a star might look like, but also a mixture of what some hot gas and ionized gas might look like. And so astronomers were puzzled by the nature of the great spiral nebula in Andromeda. And there are a number of these things. And so this is an image of the night sky. And for those of you with really sharp eyes, and then when I'm teaching my introductory astronomy classes, I ask the students if they can identify anything in this image. What you'll see here is actually the outline, the stars that make up what we call the Big Dipper. So it's that constellation that we're all, as those of us in the Northern Hemisphere, are all very, very familiar with. But within that region of the sky, there are a number of other objects that were discovered by Charles Messier when he was pointing his telescope at the night sky, looking for things that were fuzzy. He was really looking for things that were fuzzy and moved, i.e. comets. But he discovered these other objects, and they're cataloged here, M101, M109, M97, as well as M51. If we take a better look at this thing called M51, it looks like this. Again, another great spiral nebula. Now, this is more of a modern image of what M51 looks like. But the great debate in astronomy 100 years ago was about the nature of these spiral nebulae. What were they? From one point of view, looking at an image like this, some said, that looks like it's actually a planetary system in formation. Right? We see this bright thing in the middle with a spiral around it. So maybe that's planets in formation. Maybe that's a Jupiter-like thing over there to the left. So maybe it is a planetary system somewhat like our own. Others looked at this and said, no, that is what we were going to call an island universe. And that phrase comes from the notion that everything that we see in the night sky was believed to be contained in this thing that we call the Milky Way. And so the spiral nebulae, by this perspective, were things like the Milky Way, but just much farther away. And so they begot the name island universes. And this led to a great debate about understanding the nature of these objects. Were they sort of planetary systems in formation and therefore nearby? Or were they island universes like the Milky Way, but just very far away? And you can imagine the profound implication of that difference. If they are island universes, then the universe is very, very large indeed. If they're within the Milky Way, the universe is much more finite. Right? And so this was the great debate. And in the early 1900s, as I say, this debate was going on, and the central issue around it was the inability of astronomers to measure distances to objects in the night sky. And it remains a challenge for astronomy is measuring accurate distances. The only true accurate distances we can measure is with a technique called parallax, which you can simulate at home by simply sticking your arm out in front of you with your finger pointed and blinking your eyes. You'll notice that your finger moves a little bit as you view from one eye or the other. If you understand the separation between your eyes and you can measure how much your finger shifts, you can actually measure the distance to your finger. It's not the most effective way of measuring the length of your arm, but it will work. So astronomers could do that with nearby objects to measure distances sort of very, very exactly. But for faraway objects, no, we could not measure distances to these things. The resolution of this debate came with Edwin Hubble in the 1920s, using a brand new telescope outside of the small town of Los Angeles, California. Discovered a special type of star in that Andromeda spiral nebula. And that discovery led to the conclusion that Andromeda indeed was very far away. And so the spiral nebula were in fact these island universes. We have since changed that phrasing of island universes and we call them galaxies. And so the 1920s were really the discovery of galaxies and the profound implication that the universe is very, very large. And so over the course of the years of discovery of that distance, you can imagine that the concept of the scale of the universe grew tremendously. Hubble had a few other discoveries, and his subsequent discovery is one of the most important ones, I think, certainly in astronomy and perhaps in all of science. A discovery that there was a correlation between how far away these galaxies were and their velocity with respect to us. What Hubble discovered was that the farther away a galaxy was, the faster it was moving. And all of the galaxies, by and large, vast majority of the galaxies, were all moving away from the Earth. It's a remarkable discovery that the farther away an object is, one of these galaxies, the faster it is moving. And that was a tremendous discovery, and it led to the notion of the Big Bang. And the way to interpret Hubble's result was that the universe is expanding. The universe is getting bigger. And what that means is that the universe is expanding, and as it expands, it carries the galaxies with it. So don't get in your head the sense that the galaxies are moving through the universe. No, it really is that the fabric of space, the fabric of space-time, is expanding and carrying the galaxies along for the ride. And so the separation between the galaxies is increasing with time. And so then if you think about that expanding universe and say, wow, if I run the movie backwards, what do I get? If I run the movie backwards, then the universe must have been smaller in the past. And let me keep running that movie backwards all the way and say that it must at some point have begun when the universe was so small, but that all the matter and all the universe was compressed in this tiny, tiny, tiny volume. Everything that we know of in the universe was in a tiny volume, and it must have been very hot. It must have been very dense. And that is the notion of the Big Bang, the beginning of the universe. That it began with this rapid expansion of space and time in a sense that we are still seeing today. In the earliest moments of the Big Bang, it's our colleagues in fundamental particle physics who must tell us how the universe and how matter behave, because these are densities and energies that we cannot observe. The universe is hidden from us in its earliest days, but it really is something that is really the realm of particle physics. And we've got great colleagues who are doing that work. But let's kind of pick up the story about 400,000 years after the Big Bang. And that's a moment when the universe is expanded enough that it is cooled enough that we can then, that the light from that moment can travel far enough and we can detect it and look back at what we are seeing. And so the farthest back in time we can see is something called the cosmic microwave background, which represents the universe in its very earliest moments. It's about 400,000 years old. As an aside, I'll mention that one of the really, really neat things about astronomy, because of the finite velocity of light, that the farther away an object is, by the time its light reaches us, that light has traveled across a great distance. The light has been traveling for a very, very long time. And so as astronomers look farther out into space, we're not just seeing more distant objects, we're actually seeing what the universe looked like in the past. And that's one of the remarkable things about astronomy, is that we have this sense of being able to probe the earliest years of the universe because of that finite velocity of the speed of light. So what does a microwave background look like? And this is an image of it taken from a satellite. The color scheme here is representing two things. One is density of matter, so the density of the stuff in the universe. And the other one is the temperature of that stuff in the universe. And the scheme here has been exaggerated to overemphasize differences. But this background is remarkably, stunningly smooth. So the universe starts out with these tiny, tiny, tiny fluctuations in an otherwise remarkably smooth space. And our challenge as astronomers, for those of us who work on the evolution of galaxies, is to understand how the universe potentially got from what it looked like this, as this 400,000 years after the Big Bang, to a universe that we now observe using our telescopes, a universe that is remarkably lumpy. And those lumps are galaxies. And the images that you see here all come from the Hubble Space Telescope, which is a remarkable facility orbiting the Earth. And the astronomical community, again, as another bit of an aside, is eagerly anticipating the successor to the Hubble Space Telescope, something called the James Webb Space Telescope, which is due to be launched later this year. By launching Hubble above the atmosphere, astronomers got a remarkably clear view of the universe. And what we see are all of these objects out there. And these, by and large, everything that you see here, there's a few exceptions to that. And those of you with a keen eye can see a few stars in there. But what you see here are island universes. They are the galaxies. And we want to know, how did the universe get from that microwave background, which is very, very smooth with some small fluctuations, to this very lumpy universe that we now observe. And here's a schematic of the history of the universe. 13.8 billion years, all in one nice graphic. We had the Big Bang there on the left. And you see the universe expands rapidly. And at 400,000 years ago, or 400,000 years after the Big Bang, you see this what we call the microwave background. It's a period of, also known as recombination. And then the universe entered what astronomers have described as the dark ages. Those dark ages are such that the universe was dense enough that any light could not travel very far. And so light doesn't escape from that. It bounces into other matter and gets absorbed. And so we know very, very little about the dark ages of the universe. And then something like 100 million, 150, 200 million years after the Big Bang, the first object turned on. It may have been accretion onto a black hole. It may have been a supermassive star. We don't know. So this is one of those areas of research that astronomers are really trying to push to understand what were the very first things that formed in the universe. But we do know that those very first things that formed were so hot and had so much light that they began to ionize the universe. So the universe became reionized. And what that means for us is that the universe becomes transparent, that light can now travel through space and ultimately through time to reach our very telescopes. And there's a period in there of reionization where it goes from being the dark ages to being fully ionized, and they're sort of somewhat fully transparent. And that's the evolution of the universe. And so for the last 12.5 billion years, the universe has been evolving in a way that galaxies have formed. The universe has been fully transparent, and we end up with the universe that we see today nearby. This is slightly a different way of looking at it, and I've just sort of flipped the axis. So the Big Bang is now on the right, and present day with the Hubble Space Telescope is there on the left. So this is the history of the universe, and we really want to know how galaxies formed in this, and what does that mean? This slide shows that a couple of the very, very distant objects that Hubble Space Telescope has been able to detect. And we do really hope that the James Webb Space Telescope will actually probe farther to the right on this slide to see even perhaps those very first stars that formed in the universe. So I want to talk a little bit about matter. What is the universe made out of? One of the courses I've had the pleasure of teaching here at UW-Madison is a course we call the History of Matter in the Universe. We go from the Big Bang to rocks on Earth and how that transformation has taken place. But the history of matter in the universe is really a story of accumulation of how galaxies formed out of gas, how galaxies have turned some of that gas into stars. And then we ask our question, well, what happened to matter that never made it into a galaxy? Or is that galaxy formation process 100% efficient? And so that all the gas flows into galaxies. So we want to explore the history of matter. One of the exciting, but perhaps somewhat embarrassing aspects of astrophysics today is our understanding of what the universe is made of. This is a pie chart, as we call it, that shows the stuff in the universe. And what you'll notice is that over 70% of it is a stuff called dark energy. We don't know what dark energy is. It is driving an acceleration of the expansion of the universe, but we don't know what it is. You'll see another quarter of this pie chart is dark matter. We know dark matter by the impact it has on things that move. It has mass. Therefore, gravity behaves as we expect, and it causes motion. So we know it's there. We know this dark matter exists, but we don't know what that is either. What we do know about the universe is tucked into that sort of 4.5 to 5% of the universe, and that is the stuff you and I are made out of, the normal matter. We use the word baryons to describe this normal stuff. And that's what we see. That's what we look at. That's every picture you've seen of anything astronomical is reflecting some of that normal stuff, those baryons. So I want to focus on that narrow slice of this pie, the baryonic content of the universe. So what do we know about the baryonic content of the universe? And so we know that some of it is stuck in stars. We see the stars, so that must contain a chunk of the baryons. It's about 10% of all the normal stuff in the universe is in baryons, right? Sorry, in stars. 0.4% of the total density of the universe is in stars. We know that there is what we call cold atomic and molecular gas. And this is gas that we now know makes up those dark places in the Milky Way. That's molecular gas. And some of those molecules are quite familiar. CO, a little bit of methane, other more complex molecules. So some of the baryons are actually in molecules in the universe. There's a great discovery from a few years ago that some of these molecules are actually vinyl. And so we make the joke that all of your old records are now vinyl in space, but no, there are molecules in space. There's also hydrogen gas, which is relatively cool. That makes up, about 1.5% of the baryons in the universe. And what I have a picture in the bottom are the ways we can detect this stuff. One is with an optical telescope like SALT, and on the right is an image of something called Meerkat, which is a radio telescope in South Africa. And I'll return to that in a moment. And then what we see, we ask ourselves, well, we took care of the stars, we took care of the cold atomic gas. Well, where's the rest of the baryons? Where's the rest of the normal matter in the universe? The answer is that it lies in between the galaxies. And we call this the intergalactic medium. And so most of the matter in the universe, most of the normal stuff, most of the atoms that you and I are familiar with in the universe reside in the vast spaces in between the galaxies that we have identified. So here's a picture of a map of the universe, looking at the distribution of galaxies. And you can see that distribution has some structure to it. There are a lot of galaxies, but it's that space in between the galaxies where a lot of the matter is that we want to talk about. So how do we see this? How do we find this stuff? Well, there's a couple of ways. One, we can hope that it emits its own light. That's a possibility. Maybe it will influence the light moving through it. Both of these things depend upon the temperature of the gas, it depends on the density of the gas, and depends on the chemical composition of the gas, what it's made out of. And so when we do look out with an X-ray telescope, we do actually begin to see some of this gas in between the galaxies when it is particularly hot. What you're seeing here in sort of this purplish pink coloring is the image of X-ray emitting gas with temperatures well over 1 million degrees, maybe even 10 million degrees, that resides in between galaxies, particularly galaxies in clusters. So when the environment gets very dense, galaxies get much closer together to one another, the gas in between the galaxies seems to heat up and then glow in the X-ray part of the spectrum, and we can launch an X-ray satellite and detect this stuff. So we see some of this gas in this X-ray. We detect some of it others by what I'm going to call a cosmic lighthouse. And the image here kind of shows that on the right, you see something called a quasar, very, very bright object. And if we can observe that quasar that might be very, very far away, and we can observe it in a way using a technique called spectroscopy, what that allows us to do is to see the signature of whatever is between us and the quasar. And that shows up in this series of lines you see in the spectrum at the bottom of this slide. Each one of those has a distinctive chemical signature, tells us something about the gas in between us and that quasar. And of course, the farther away the quasar is, the more volume you're probing through the universe. And so you can detect the presence of stuff in between the galaxies by finding these lighthouses and doing this technique to identify some of that material. And we have done that quite successfully. Here's an example of another case where folks looked at this quasar there on the left and detected a bunch of gas, and the A, B, and C are just the different pointings of the telescope there on the left. That sort of gray shape you see implies the distribution of intergalactic gas that is actually very far away, though at the same distance, but very far away, of a nearby galaxy, this thing NGVLA, there you see in the upper right. So this is a nice detection of the presence of gas in between galaxies, sort of within the neighborhood of a galaxy, but not necessarily associated with that galaxy. So the problem that we have is that there actually aren't that many lighthouses to use. And so we can't accurately map the full distribution of this gas in between the galaxies doing this. So astronomers seek a different tool. And the one I want to point out today is one of my favorite, one of the most powerful objects in the universe. And those are things called radio galaxies. This is an image that combines an optical image of the sky. So you're seeing what your eyes would be seeing with an optical telescope. There's lots of galaxies. There's a few stars near the very bright thing there you see is a star. In the middle of the image is a very large elliptical galaxy. The pinkish white material you see coming out of that galaxy is a radio jet. And so that image comes from the Karl Jansky Very Large Array in New Mexico. It's showing you what the sky looks like if your eyes were sensitive to radio emission. And what you'll notice is that these two jets seem to come out of this galaxy and then billow out in these very, very large lobes around the galaxy, outside of the galaxy. These are remarkably powerful things powered by ultimately accretion onto a supermassive black hole in the center of the galaxy. But sometimes the jets are bent. In the previous image, you'll notice that those jets are straight. But occasionally we see objects, and this is the way astronomers like to look at things, where those jets are actually curved. There's an object on the right there, you see those contours are showing you that radio jet, showing you that it's bent. On the left is a radio image showing you the bent jets. I've got a few more examples of those. Here is another sort of a rogues gallery of a collection of these things we call bent doubles. Here's another one. The contours, again, are what we see with a radio telescope. The blue-green image is what we might see with an optical telescope. And again, what you see is that the radio emission, those jets and those lobes, are curved. And that's important. Here's another example of one of those. So what does that curvature mean? And don't worry too much about the math on this. But what we think is going on is that curvature is caused by ram pressure. So what's ram pressure? If you're driving down the highway and you stick your arm out of your window of your car, what you'll feel is that your arm wants to bend back. Right? That's the pressure of that air pushing on your arm, causing it to bend back. And that's ram pressure. And so we can interpret the curvature, the bending of those jets, as ram pressure of that galaxy moving through some intergalactic medium. And if we can measure the curvature of the jet, how bent it is, if we can measure the velocity with which it is moving, and if we can measure the velocity, not just of the jet, but also the velocity of the other objects around it, then we can calculate the density of the gas it is moving through. And so this becomes a technique for detecting not just the presence of the intergalactic medium, not just the presence of all those baryons, but actually measuring the density, how much stuff there is in a given volume. And we've begun to do this using a multiple of techniques. And I'll show you an example here at the top of the slide shows you one of those bent jets. Again, the contours are what we get from a radio telescope, like the VLA there at the bottom left. The black and white is what we see in an optical telescope. So you can see the galaxy there in the middle that this bent double is associated with. We then take a bigger view and move back out, and we'll notice that it is associated with a number of other galaxies in the neighborhood. This is in a galaxy group. And we can measure the velocities of all of those different galaxies. And that ends up there on the right, shows sort of a histogram. And we have to measure the velocities using an optical telescope. We've got an example of that, the WIN telescope, another telescope that the University of Wisconsin is involved in on Kitt Peak National Observatory in Tucson, Arizona. And so we can combine these two techniques, the radio telescope that you see in the bottom left, the optical telescope you see in the bottom right, combine those two techniques, get the data that we need to be able to do these calculations to measure the density of the intergalactic medium. And we've done this, and this is a remarkable result here. And what we see here, it's sort of a complicated plot. But what I want you to notice is that horizontal line that goes right through that. That is what we think the baryonic content of the universe should be. okay, based on that pie chart that I showed you along a few slides ago. The black squares, the bottom half, were a result of people trying to find those baryons and not quite getting the right number based on the stars, the cold gas, and even that hot gas that I showed you an image of. But if our results were to be verified, we've identified that these baryons, these missing baryons, do in fact reside in between the galaxies. And that's a great result. So that leaves us in an interesting point. The galaxies are residing sort of within this bath of gas that they're moving through, and that sometimes that has an impact on the galaxy. And going back to that very first question of the evolution of galaxies, we can ask ourselves, well, how do galaxies actually acquire the gas? And I want to take a bit of an aside here that the gas is kind of like the fuel to form stars. Stars, like our own sun, form out of collections of gas, molecular gas and atomic gas. Galaxies need that fuel to make stars. And one of the big questions in extragalactic astronomy, those of us who study galaxies, is this question of how do the galaxies acquire that gas? How do they get the fuel that they need to make stars? Here's another lovely galaxy. This is a nearby galaxy. You can see it in all of its glory. So making stars requires cold gas. The gas has to be dense and cold for the molecules to begin to stick together and collapse, and self-gravity takes over to make a star. This intergalactic medium that I've mentioned, this gas between the galaxies, is hot. It's probably hundreds of thousands of degrees. Not so hot that it glows in the X-rays, but it's pretty hot. So how does it go from that form into that form of being cold gas in a galaxy? And this is where something called the cosmic web comes in. And this is it's a simulation of the cosmic web. And what you see here in all of these colors is just meaning to suggest that the regions in between the galaxies are complex. It's a complex network, and the streams that you see, the blue, particularly the blue streams, seems to be how gas is funneled onto a galaxy. And so there is this mechanism that we don't yet fully understand by which gas comes from the intergalactic medium along this cosmic web and flows into galaxies to form galaxies and to provide galaxies with the fuel they need to make stars. We'd love to see this in action. We'd love to get the observations that would actually show us how this is happening. So how do we go about doing it? How do we go about mapping this transition? And that's where another project I'm involved in comes in, something called Chilies. And we love the logo there is a nice chili pepper. It's a Cosmos H1 large extragalactic survey. One thing you should know about astronomers is we love our acronyms. Everything has to have an acronym. It's a telescope, it's a survey, whatever it is, you've got to have an acronym. So we have Chilies. What Chilies is that we took 1,000 hours of telescope time using the Very Large Array in New Mexico. And we pointed it at a single point in the sky for 1,000 hours, spread out over a number of years, in order to see if we could measure the cool gas, that material that actually out of which stars are made, if we could actually see that process of that gas coming into galaxies. That was the point of doing Chilies. It's also the very first of a number of really large surveys that the radio astronomy community is embarking on today. And so with Chilies, you can see this is the very long line here, we managed to go very, very far out into space to probe using Chilies, to understand the evolution of this neutral hydrogen content. That's what that H1 means, neutral hydrogen. Hydrogen is the simplest of atoms, a proton and an electron. And we are looking for signatures. It's the most common atom in the universe. Most of the atoms are actually neutral hydrogen atoms. And we are able to probe that with a radio telescope. And so this is a somewhat complicated plot, but in other words, just showing you the gray dots there are the distribution of galaxies. The red dots are where we detected this neutral hydrogen gas. And the images with the nice purple contours show you some of that distribution of the gas centered on galaxies, but often really elongated and twisted and distorted. And that might be the signature of the accretion of gas from the intergalactic medium onto a galaxy. There's just a few more examples of that from a pilot. We're at the final stage of getting all 1,000 hours put together to really have that first 1,000-hour view of the H1 content of the nearby universe in this one point on the sky, when we expect to be done sometime later this year. We don't know yet whether this actually is a signature of the accretion of gas from the intergalactic medium onto a galaxy. But hopefully in the next few years, we'll find out. And that's what keeps the science exciting, is that these questions that we can't quite answer yet require more data and more observation. So what is next? I've taken you on this very, very rapid journey, probing the gas in between galaxies. But also probing how that gas might be getting onto galaxies. And one thing about astronomers that our telescopes are large, and they're getting larger because the questions we are asking are more profound. The questions we are asking require new technology. They require different approaches. And so the community around the world, the international community, is coming together to help put together the technology needed to answer really fundamental questions about the nature of the universe. This picture here is taken of Meerkat. It's in the Karoo region of South Africa, not too far from Salt, a little bit actually about a 5-hour drive up the road from Salt, in a really wide open region of South Africa. It's called the Karoo region, and so the CAT part of it, K-A-T, stands for the Karoo Array telescope. It's a collection of radio dishes in South Africa. The Meer is the Afrikaner word for more. And so this looks like it's a larger array of telescopes that we now have in South Africa to probe some of these questions that we ask, particularly that last one about, can we map the neutral hydrogen content of galaxies? Meerkat just turned on a few years ago and is now in the midst of doing a number of really big surveys to address some of these questions. And it's a precursor to something coming even larger called the Square Kilometer Array, which will probably come online in the next decade or so. And here in the United States, we are in the process of proposing the NGVLA, the Next Generation Very Large Array, which would be centered there in New Mexico and extend out with these dishes spread in parts of Texas, Colorado, Arizona, to provide a deeper view of what the universe looks like. And I'll end with a little bit of a story. That the Very Large Array telescope, as we now know it, is the Karl Jansky Very Large Array. And Sarah, in the introduction, remarked that I had the honor of being a Jansky Fellow as a postdoc after I finished my PhD and before I came to Wisconsin. Karl Jansky is known as the founder of radio astronomy. And remarkably, maybe not remarkably, because we are great, Karl Jansky got his undergraduate degree from the University of Wisconsin. And he went from here to work at Bell Labs in New Jersey, and doing the work that he was doing in Bell Labs early in the 1930s, discovered that the center of the Milky Way was emitting radio waves. And that was really the first discovery of radio waves coming from anywhere beyond the sun. And so Karl Jansky is known as the founder of radio astronomy, and the Very Large Array is named in his honor. And it's a great honor for me to actually have shared that a little bit in my career as a Jansky Fellow. So thank you for listening. We are in an exciting time in the world of astronomy. I hope there are some questions in the chat, and we look forward to meeting again. Take care.
Wow, that is just the imagery and the way you've presented this is just really fascinating. Thank you so much, Dean Eric Wilcots, for taking time out of your busy schedule to be with us today. Hi, everybody. Fran Paleo-Moyer, Badger Talks producer. As Eric said, please post your questions in the chat. We did have a comment from Debbie Cardinal, and she was giving a shout out to Henrietta Leavitt as you were talking about Hubble. Do you have anything to say on that? So
yes, one of the really fascinating stories is that in that quest to measure the distances to astronomical objects in the early 1900s, Henrietta Leavitt and a number of other women who were working in the Harvard Observatory at the time were the ones who actually discovered a correlation between the luminosity or the brightness of a certain type of star and the periodicity of its variability. So its brightness varied over time with a certain period. That period was correlated with its brightness. And that was a discovery key to measuring the distances. And Henrietta Leavitt was the one really responsible for that. And that allows, because now measuring that period of variability was much, much easier than measuring an absolute brightness of anything. And so that allowed astronomers to begin to measure the distances to nearby galaxies. So yes, a great shout out to Henrietta Leavitt, one of the real pioneers in astronomy.
Thank you for sharing that. Bethany Riley asks, are there any repercussions from these results for direct dark matter searches?
Good question. So as I mentioned, we're looking at the pie chart. We don't know what dark matter is. There is not much here for direct detection of dark matter. These techniques are different. We can see the presence of it by measuring how things move, but direct detection of what it is, these techniques won't shed light on that.
Thank you. We have a comment from Harold Steinberg on our screens channel. Oh, and shout out to everybody watching on YouTube. It's our first time on YouTube, so welcome. So Harold says, thank you for taking the time to show us this work. You're a very good speaker and make this content very easy to understand, which I had noted early on in your presentation. You're obviously very passionate about this work and you are an excellent presenter.
Thank you.
Question for you. How did you get started and interested in astronomy? Can you give us a little bit of background on your personal story, maybe as a young person?
Sure. So my story, not unique. Not every astronomer has followed this path. I am one of those people who was fortunate enough as a kid to get fired up about astronomy, and got a telescope for Christmas at an early age. I was 8 or 9, growing up in Philadelphia. And so I would take my telescope out in the backyard in Philadelphia. You don't see a whole lot in the night sky from Philadelphia, but you do see the planets. And so that sort of really piqued my interest. At the same time, NASA had sent the Voyager missions to Jupiter and Saturn, and the images coming back from Jupiter were just blew my mind. So I was a kid and I just developed a passion for and a real deep interest in astronomy, and just was fortunate enough to pursue that passion through college and into grad school and into the career that I've had. So that I began as an 8 or 9-year-old, just getting wowed by the sky, and got a telescope for Christmas. And my dad said later on in life that it was the best $50 he ever spent.
Well, parents out there listening, hint. Let's see. Ruth Fitzgerald says, good explanation. We'll know better of astronomy when I visit a planetarium. It sounds like you're inspiring people. Kurt Meyer asks, is it possible that redshift can come from other sources in addition to recessional motion?
So redshift, good question. Redshift is how we describe the fact that an object is moving away from us with velocity, and the amount of redshift is a function of how fast it is moving away from us. The cosmological redshift is due to the expansion of the universe as a whole, and that's the little z. If you're paying close attention, there are a couple diagrams that have that at a little z. That's the cosmological expansion. So that's that redshift. Anytime when there's an object that actually is moving away from us, it will have a little bit of a redshift. And so sometimes, and this is one of you'll find cases where an object is very far away and should have this nice cosmological redshift, but because it is in itself in a cluster and it is moving within that cluster, right, it could have a bit of an additional redshift if its motion in that cluster is away from us at that particular moment. But it also could have a little bit of a blue shift if its motion within that cluster is towards us at that moment. So we do have to disentangle the local dynamics that causes galaxies to move that can add or subtract from that cosmological redshift. But if you're looking at within our own Milky Way, stars moving away from us will be redshifted, for example.
Great. Thank you for clarifying that. So I have one final question for you. If you could flash forward 100 years, what is it you hope astronomers will know and have discovered at that point?
I'm going to preface that by borrowing an analogy that I've heard elsewhere, that astronomy, science in general, is that sense of mountain climbing, that in this sense of you look nearby and you see some peak and I got to get to the top of that, right? And you get to the top of that, and then you realize, oh wait, I'm not done yet. There's more. I hope we never get to the point where we look out and say, we've got it all. Okay, so preface it with that. There are some things that I do think we are on the cusp of knowing. That is, what actually were the first objects in the universe? What were the first things that turned on in the universe 13.4 billion years ago, 13 billion years ago? So understanding the first objects, and I think then so that's one thing I hope we do know. I do hope we understand what dark matter is by then. We're going to rely on our physics friends to be able to tell us what dark matter is. So that's a key thing. I hope we know in 100 years. I think hopefully we should know that. But then more locally, and more nearby, and perhaps more and somewhat relevant to the events on Mars, that we have a rover on Mars. That fundamental question of whether life exists somewhere else. I really hope in the next 100 years we have discovered some life somewhere else other than here on Earth, and that will be a tremendous discovery.
Dean Eric Wilcots, thanks so much again for joining us today. Really
my pleasure.
With us. Well, everybody tune in next week, Tuesday, April 6th at noon, and we're going to be welcoming Erwin Goldwyn, who's a professor of horticulture. His lab works specifically with the breeding of carrots, onions, and beets. And he's going to be talking about how UW-Madison has really played a role in the selection of improved crops for Wisconsin farmers, but also gardeners and consumers. So please tune in next Tuesday. As always, visit badgertalks.wisc.edu, where you can see our list of upcoming talks. You can sign up for our email list. You can also consider a donation to Badger Talks. We are supported by grants, so we appreciate those donations. And you can also book your own speaker for events coming up. Thanks so much for tuning in, everybody. We'll see you next week.